So, what we are going to watch today is a lecture about pipelining, and actually this is the topic that we are going to cover this week. You remember that in the previous lecture, Professor Mutlu explained the single-cycle microarchitecture, the multi-cycle microarchitecture, and also microprogramming. Now the next step is the pipeline architecture. That's what we are going to cover today and tomorrow. And then next week, we will continue with out-of-order execution. So before we start with the contents, I would like to invite you to this lecture, this distinguished colloquium that will be taught by Professor Wayne Mayhew from the University of Illinois at Urbana-Champaign. Professor Hu is a pioneer in compiler design and computer architecture, and he has very important seminal work in out-of-order execution, very long instruction word architectures, and GPUs that are different topics that we are covering and we are going to cover in this course. So don't forget that this will be on April 30th, and you all are invited to come. The readings for this week and for next week, well, especially for this week, is chapter or section 7.5 in Harris and Harris. But you are encouraged to continue reading until the end of the chapter 7, because most of the things will be covered in the next week. And this is the first thing where we are going to continue. You might remember that this was the last slide that Professor Mutlu showed last week. So what we're going to do is watching this video. Have fun.
So the question to always ask is, can we do better? Never be satisfied is good if you want to get to if you want to advance the state of the art, right? And people clearly ask that after microprogram machines. I'll ask you, can we do better than this? I guess people say yes. So one limitation that I see over here is limited concurrency, right? We designed this machine, but we're really spending so many cycles to execute an instruction. 6 cycles to do a load, for example, in LC3B. And what is worse is, while you're doing a load, while you're in part of the finite state machine over here, let's see. So, for example, if you're in this state over here, when you're fetching an instruction, everything else is idle, right? So when you're accessing memory over here, the rest of the data path is basically twiddling its thumbs, waiting, doing nothing, right? That sounds like a waste, especially if you want to improve performance. Basically, that's what limited concurrency means. Idle when you're doing some operations. Okay, basically some hardware resource idle during different phases of instruction processing cycle. For example, fetch logic is idle when instruction is being decoded or executed. Most of the data path is idle when a memory access is happening. So can we actually do multiple things at the same time in the data path to improve this concurrency and hopefully improve performance, right? And the idea, of course, it's yes. Basically, why would we like more concurrency? Because we can get higher instruction throughput. Instead of executing 6 cycles per instruction or finishing 1 instruction every 6 cycles, maybe we could finish 1 instruction every cycle if we pipeline things such that while we're doing some work for this instruction, we're doing some other work for this instruction, and some other work for this instruction, and some other work for this instruction, right? That's the idea, basically. When an instruction is using some resources, process other instructions on idle resources that are not needed by that instruction. For example, when an instruction is being decoded, fetch the next instruction. When an instruction is being executed, decode another instruction, decode the next instruction. When an instruction is accessing data memory, execute the next instruction. And when an instruction is writing its result into the register file, access data memory for the next instruction. So that's the idea of pipelining, basically. And I've already given you the idea. But let me repeat it. More systematically, pipeline the execution of multiple instructions. Don't wait until the previous instruction finished. And the analogy is assembly line processing of instructions, right? Everybody goes through the assembly line, and while one instruction is later in the assembly line, another instruction is entering the assembly line. We divide the instruction processing cycle into distinct stages of processing and ensure that there are enough hardware resources to process an instruction in each stage. That's important. So we will increase the hardware resources for this. And we process a different instruction in each stage. And instructions in consecutive and program order are processed in consecutive stages. And the benefit is this increases instruction processing throughput. Basically, again, I'll repeat it. Instead of taking 6 cycles per an instruction, or finishing one instruction every 6 cycles. So if you look at this state machine over here, this one, we're finishing one instruction. If it's an add instruction, we're finishing one instruction. Oh, sorry. Yes. Thank you. This should remember the last state it's in. That's prediction, right? We will talk about that. But basically, still doesn't work? Why is that? How about this? Now I can see if it works. So 1, 2, 3, 4, 5. Basically 5 cycles. Actually, if memory takes longer, maybe 10 cycles, right? Depending on how long the memory takes. So instead of finishing one instruction every 10 cycles, hopefully we'll finish one instruction every cycle, because we'll be putting one instruction into the pipeline every cycle. So that's the idea over here. And if you have multiple pipelines that are operating in parallel, maybe you can fit more than one instruction per cycle, right? If you have 5 parallel pipelines or 4 parallel pipelines, you finish 4 instructions per cycle. That's how you can improve performance significantly. Okay, let's go back. So that's the benefit, hopefully. But we'll see a lot of gotchas in this. The downside, start thinking about this. There's always a downside. So we're going to add more hardware cost. We're going to add more overhead. And we're going to take each instruction take longer to be able to do this. So let's look at the beautiful case first. Multi-cycle looks like this. Let's assume that you take always 4 cycles per instruction. Let's assume that these are independent add instructions. It looks like this, basically. First instruction finishes in 4 cycles, next instruction 4 cycles. So you take about 12 cycles to finish 4 instructions. You'll see how stupid this is when I give you the next analogy. But if you pipeline it, this is what you get, basically. When you're decoding the first instruction, you fetch the next one. When you're executing the first instruction, you're decoding the next one, and you're fetching the next one. And this is where the pipeline is full. This is called a full pipeline. All of the stages in the processing are occupied by instructions that are hopefully useful. Right? Now, at the steady state, you're finishing 4 instructions per cycle. Basically, you're processing 4 instructions in one cycle. But in the steady state over here, you're really finishing 1 instruction per cycle, or 4 instructions in 4 cycles. Make sense? But of course, life is not always this beautiful. But this is the beautiful case. Ideally, with an ideal pipeline, this is what you would get in terms of throughput. But there are a lot of non-idealities in other things also. And we'll talk about those non-idealities and how to handle them. Okay, let me give you the analogy to show you how multi-cycle is so stupid, right? I just convinced you that a multi-cycle is good. But now let's see why it's so stupid. So assume that you have a bunch of clothes, dirty clothes, to finish. And you want to do them separately. Do you do them this way? First of all, you first put stuff into the washer, and then when the washer is finished, put it into the dryer, and then fold them, and then put the clothes away, or ask your roommate to do the stuff. Whatever, basically 4 different steps, each taking 30 minutes. You do them, and then only after that, you start the next load. That sounds stupid, right? You wouldn't do that as a human being. Why are we putting machines doing independent loads, independent instructions this way? It's essentially a multi-cycle machine. So you've spent your beautiful evening doing 4 loads of laundry. That sounds terrible. Now, if you can offload it to your roommate, your poor roommate has spent some of his or her evening to do this. So here, it looks like an instruction, actually. The steps to do a load are sequentially dependent. You're not going to put things into the dryer before you wash them. You could, but that defeats the purpose, probably, of doing laundry. And you're not going to fold them before you dry them. And you're not going to put them into your closet before you fold them. I guess you could skip the steps. Not all instructions have the same steps. Not all programs have the same requirements, right? But there's clearly a sequential dependence within an instruction. And across different loads, across different instructions, there is no dependence, right? You could start this load right after you move it to the dryer. There's no dependence between these two, between these four, actually. Like this, I cannot imagine. Different steps do not share resources, right? There's no resource sharing. The washer and dryer are completely separate. So as a result, you can perfectly pipeline this. Basically, this is what a pipelined processing of laundry looks like, right? Once the first load finishes in the washer, you put it into the dryer, but you also start the second load in the washer. And ... You can see the idea. So you do 4 loads of laundry in parallel in the steady state. So if you look at the steady state, this is what's happening. No additional resources are needed over here. Throughput is increased by 4, as you can see, and you have the rest of your evening to enjoy. Study computer architecture. That's what enjoy means, right? At least for me. I guess that's not that funny for all of you who are waiting for the Easter break. And latency per load is the same. As you can see, we didn't increase the latency. Of course, it's a perfect case. We will see that we will increase the latency in instruction processing. But let's see one example over here. Who has experience in doing laundry here? Who has done their own laundry? Okay, good. And which stage actually takes the longest? Anybody? The washer, the dryer, the folding? Dryer, yeah? That damn dryer. That always takes the longest. And I agree with you. It always takes the longest, and as a result, it causes an imperfect pipeline over here. Now, we could go into the mechanics of the dryer and why it takes longer and ... but we're not going to do that over here. One way is to fix the dryer such that it doesn't take long. But if it takes long, now you have this problem, right? The slowest stage decides your throughput because you cannot put stuff into the dryer before the dryer finishes the first load, right? As a result, your throughput reduces. Instead of finishing your laundry at 9:30 over here, you finish it at 11:30 over here. Now, how do you fix this problem? The same thing happens with instructions as well, right? If your register file access takes 2 cycles, you have the same problem, right? How do you fix this problem? Have a faster dryer. That's one solution. Say it again? Buy another one. Excellent. Buy another dryer. Right? Using 2 dryers, now you restored the throughput, right? Dryer A, dryer B. Now, if you want to have a high throughput pipeline, you add hardware, basically. That's the takeaway. Okay, so an ideal pipeline would increase throughput with little increase in cost. Unfortunately, that's not always possible, so we're going to add hardware cost. But let's look at an ideal pipeline. What do you need? Basically, for the pipeline to be ideal, we want to repeat the identical operations, meaning the same operations repeated on a large number of different inputs. For example, laundry loads always go through the same steps. Washing is repeated on many, many loads. Drying is repeated on many, many loads. Instructions, fetch is repeated on many, many instructions. Decode is repeated on many, many instructions. So the more steps you have that are identical across instructions, the better you are. Because you're utilizing the same hardware to process many different instructions. Independence is very important. You should not have dependencies between repeated operations. Basically, the loads, you can pipeline them very well because they're independent of each other. If the instructions are independent, that's good. But if they're dependent on each other, if you need to do a multiply that's dependent on an add, now you've added a dependency and you may not be able to really start the multiply. If you have a multiply that needs the result of a load, well, you may not be able to start the multiply, right, before the load result is available. So now they're not perfectly independent of each other. If the load takes 500 cycles especially, right, now you have a problem. So this is clearly very important. Well, there's another problem with instruction processing. How do you know which instruction to fetch next? right? If you're going sequentially, that's good. But what if you have a branch instruction that's dependent on a data, branch equal, for example, in MIPS, and you need to resolve that branch? You cannot even figure out what to put into the pipeline at that point, right? So you can guess. You can say, oh, I'm not going to take this branch, so I'm going to keep going sequentially. But that's a guess. You need to verify that guess, and if you're wrong, you need to flush the pipeline. So now you're seeing the issue of dependence, right? This is control dependence, which is different from data dependence. It's really a special case of data dependence, really. So independent operations is critical, but we're not going to get that. That's why life is not as good. And the third requirement for an ideal pipeline is uniformly partitionable sub-operations. Basically, processing can be evenly divided into uniform latency sub-operations. And this is basically a balanced pipeline. Fetch takes the same amount of time as decode, the same amount of time as the next stage, the same amount of time as the next stage, the same amount of time as the next stage. And because it's happening in a single clock cycle. Now, if for some reason decode is much faster, it doesn't need the entire clock cycle, you're really wasting that clock cycle, right? You didn't uniformly partition your sub-operations. As a result, you really pipeline things, but you really don't need that much time to finish that sub-operation, to finish the decode. So you wasted your clock cycle, which means that your pipeline is not balanced in this case. Now, we saw this problem in multi-cycle architecture also. This is essentially a problem of balancing the critical paths. It's not only the critical paths, because critical path may be the worst case, but it's really the operation that you're doing. So you could be increasing the processing latency of an instruction because of this. And we will see that. So it's not clear if these are ideal pipelines, but the example that I gave you in doing laundry is an ideal pipeline. Automobile assembly, I'm not sure. But clearly, instruction processing cycle is not an ideal pipeline. So let's look at the lower level view of this. Basically, we have this is a single cycle machine, if you look at this. And we basically execute different portions of the instruction processing within a cycle. Let's call it T picoseconds, right? Your bandwidth or throughput is 1 over T in this case. Now, if we have two pipeline stages and somehow partition them, ideally we would like our bandwidth to be 2 over T. And if we partition them into 3, ideally we would like that to be 3 over T, right? That sounds beautiful. Now, the problem is there are a lot of overheads over here. At the hardware level, you basically have a latch delay. It's not just the T, this combination logic delay, but there's also the latch delay. So your throughput is really 1 divided by T plus S, where S is the latch delay. Now, if you do a pipelined version over here, each stage's throughput is 1 divided by the T divided by K picoseconds plus the delay over here. So if you think about it, the maximum bandwidth that you can get is the minimum logic over here, minimum combination logic is 1 gate delay, plus you still pay the latching overhead. So if you think about it from a throughput perspective, your throughput is really limited by the latching delay, latching overheads, plus the minimum combination logic delay. So how minimum can you make this combination logic determines the extent of your pipelining, but usually your performance degrades much earlier than this 1 gate. So people have argued, for example, you should really have about 8 gates or so to have an ideal pipeline. But anyway, you don't need to know about that. Now, another thing to note over here, as you add stages over here, you're really accumulating this latch delay. So if you add latch delay, basically reduces throughput because it has switching overhead between stages, but it also increases your latency, right? For example, let's say you have 20 different pipeline stages over here. Your latency is not just T picoseconds plus S, it's really T picoseconds plus 20S, right? That's how long it takes to execute an instruction. Now you increase your latency. And what is worse is, it's not just, because you cannot uniformly divide. This is the uniformly partitionable sub-operations. Let's say K is 20 stages. It's not that this will take T over 20 picoseconds. You'd be very happy if it does. It usually takes longer than that, actually. So let's say this takes T over 15 picoseconds. Now, instead, you multiply that by 20, so you have 20T divided by 15. So you increase the processing time in the combinational logic, plus you've added latch delay for 20 of those stages. So you really increased your latency of processing. The argument is if you can keep the pipeline full, your throughput remains the same, but your latency increases for each instruction. So if your throughput remains the same, that's good, right? So overall program execution time will hopefully reduce, but individual instruction latency increases. And again, this is a very fundamental trade-off between throughput and latency in pipelines. Okay, so there's also a cost aspect of this. If you look at this non-pipeline version, the cost is number of gates that you have, let's say, and the latch cost. But if you have a k-stage perfectly pipeline version, hopefully you'll divide the g gates for each stage to g divided by k. Again, that's perfect. That's very hard to achieve. But your latch overhead jumps up the roof again, right? If you have L stages over here, you pay the latch overhead for every stage. And if you have big latches, we will see why it will become big soon, because we will need to propagate the control signals in a pipeline. This will become relatively high. So we're going to add hardware cost. If not for the combinational logic, which we will also add, definitely for the latching overhead. So latches increase hardware cost. So nothing comes at a cost, basically. So let's look at the pipelining instruction processing a little bit. You've seen this before. This is the instruction processing cycle, and we're going to divide it into 5 stages, again, arbitrary. People spend a lot of time balancing the pipeline stages in real life. We're not going to do that. So this is one of the single cycle architectures that we've seen. You don't need to exactly bother about exactly how it looks, but they look all similar, as I've shown you in the single cycle recap. We divided this into stages, basically. This is what it looks like. And we decided our clock cycle time is about 200 picoseconds. Now, immediately, there's a stage that really doesn't need 200 picoseconds. It turns out it needs only 100 picoseconds. Well, we basically given up the remaining 100 picoseconds over there. We've wasted 100 picoseconds per instruction. Too bad. That's what happens if you don't balance your pipeline stages. And again, there's another one over here. Right. And you need to be very careful about these loops that go through boundaries, right? Here in the single cycle, you basically update the program counter. Now you're fetching something. How do you update the program counter at the same time? You need to be very careful about those things. So, for example, here we're going to write back to the register file. We need to use the right register ID, correct register ID as the destination register. It cannot come from this stage. It has to come from this stage, right? Because the instruction has moved to the stage, which means that you need to carry with the instruction every single thing that you will need in the future. The register ID that you're going to store something into, you'd better carry it to the write back stage, such that you write back to the right register. That now increases the amount of logic that you need to add, both in terms of buses as well as registers. Okay, let's assume we divide into stages this way: fetch, decode, register file read, execute address calculation, memory access, and write back. And this is the register file write that's kind of emulated over here, but we'll talk about that. And ignore that for now. We'll go about that. There are many questions. Is this the correct partitioning? Maybe not. Why not 4 or 6 stages? Why not different boundaries? And that's where some of the art comes in. Maybe sometimes by increasing the number of stages, you can actually get better performance, right? Because you divide things better. If you have 2-stage pipeline, dividing things better might be difficult. But increasing the number of stages, you clearly add more overhead also. But you could eventually end up with a better performance. So let's look at the throughput of this pipeline. Remember, we divided into 1, 2, 3, 4, 5 stages. So ideally, we expect 5x throughput, right? I'm going to give you three instructions that are independent of each other. 3 loads. This is the single cycle, and this is the performance improvement you get with a pipeline. This is how long it takes. Single cycle machine takes about 2400 picoseconds. But the good thing is the single cycle machine spends only as much time as the sub operation needs. So the register file access needs 100 picoseconds, you spend only 100 picoseconds. In the pipeline machine, you spend 200 picoseconds because that's the stage dedicated to register file access, right? So if you look at this, pipeline looks good, it's faster, but it's not 5 times faster, it's really 4 times faster in this case. In the steady state, if you do the steady state calculation over here. Why? Well, because of this, basically. We're really wasting this, this part of this cycle and this part of this write-back cycle. We didn't partition things well. And this is a really, really ideal example. As you can see, it doesn't even include the latch overheads, right? Here I didn't, I said that we didn't add a latch overhead over here. Okay, so we need to add pipeline registers. So to take the single cycle architecture and pipeline it like this, we need to add pipeline registers at the end of each stage. And we did this for the multi-cycle architecture, so it's going to be very similar. But we're going to look at pipeline control. So examples, basically you need to put the instruction register over here, instruction, and PC+4 over here, and all of the other things that you read the stuff that you read from the register file, the immediate, and other things over here. The data that you read from memory and the ALU's output over here, so that you can write it back. But you need, and clearly no resources used by more than one stage, but there will be loops that you need to handle carefully. And all instruction classes must follow the same path and the timing through the pipeline stages. So let's take an example. This is a load word. You fetch it, you decode it, you address generate over here, and then you access memory, and then you write it back. So load word is good because it uses all of the stages, right? Okay. Yeah, load word, exactly. So this is what I mentioned earlier. Basically, when you write back, you need to use the correct register number, which really needs to come from here. The destination register, you should have, when you decoded load word, you should have kept the destination register number, propagated it, and when the load word comes here, you should use that destination register number and the associated control signal to write into that destination register to place the data that you loaded into the destination register. Make sense? So you need to use the right data and right control at the right stage. Okay, hopefully this is clear. Well, we've just talked about any performance impact, so this is referring to this part. Some instructions don't need all the stages, right? For example, an ALU operation doesn't really need to access memory, yet it's still going through that memory access stage. Well, too bad, right? Again, that's the cost of pipelining. It needs to go through this memory access stage, waste 200 picoseconds, because the alternative is bad. The alternative is you need to remove it somehow from the pipeline and handle it. But we're going to talk about something like that later on. Basically, there's a performance impact because that instruction could have potentially finished earlier, but then it would break the pipeline, right? If you actually finish it earlier and do something else, basically write its result back over here, now you have another issue. If there is another instruction over here, a load instruction that's writing to this register, and there's another add instruction that's trying to write to that register from this stage, which one takes precedence? Which one writes? Okay, think about this. This is actually a dependency that you need to resolve in a pipeline. Okay, this is another example. Again, two independent instructions, load and sub, go through the pipeline nicely, but this sub basically does nothing during this memory stage, right? Life is not always this beautiful, unfortunately. Let me give you some beautiful pictures. This is basically what, to define some terms. This is steady state, as I've shown you. Full pipeline, you have instructions over here, and you have time over here. And over time, instructions flow through different stages, and once you fill the pipeline, it looks beautiful like this. Right? This is another view. This is the resource view of it. Basically, these are different stages, and these are different time steps, and this is what it's processing at that time, right? Different instructions. This is very simple, and a full pipeline looks beautiful, but the problem is we're not going to have a full pipeline most of the time. That sounds sad, right? You design this pipeline, and we're going to try to make it full later on. So, okay, basically the control points that we have are identical as a single cycle data path. There's nothing really that different because we're controlling the same data path, except we've added some things to the, like the registers. So, what kind of control signals do we want? For a given instruction, we have the same control signals, but control signals are required at different cycles, right? Depending on the stage. For example, when you're writing to the register, that control signal is required at that time. It's not required earlier, but you need to carry it with you. So there are two options here. One is decoding once using the same logic as a single cycle control logic and buffer the signals until we have consumed them. It looks like this, basically. We have a huge decoder over here based on the instruction that generates the control signals as much as possible. And these control signals are generated for this execute stage, this memory stage, and this write-back stage. And initially, you store them all at this pipeline register, so it looks huge. And then the control signals that are consumed by that stage don't get propagated. But new control signals may potentially be generated. So you can see that the control signals that are needed for write-back are propagated to this stage, and then they're propagated to the write-back stage, and then they're used over here. Right? Make sense? So now we're adding more to the registers, pipeline registers. They're becoming bigger. And if you have a huge instruction set, this may be a huge pipeline register over here. Or another option is to do local decoding. So this is decoding globally, if you will, once. Or you can carry relevant instruction words and fields down the pipeline and decode locally within each or in a previous stage. Now, if you remember my, what is that? My principle. Yeah, basic principle. You would rather decode in a previous stage, right? You basically carry some of the instruction and you do some local decoding over here to generate the control signals that are needed for this stage. That way you can get rid of the overhead of some of these registers a little bit, but now you add more combinational logic. Basically, you distribute your control logic or decoding across the stages, which may not be a bad option, actually, as long as you can do that. So which one's better? The answer is it depends. Basically, it depends on the design and what you're constrained with, right? Sometimes it may be better to generate the control signals than just propagate them. That sounds simple, right? Okay, so these are the pipeline control signals. Again, this basically shows that you have a control logic that generates different control signals for the different stages, and you propagate them. You can see that the ALU op control signal is used from this X part, execute part, and some of the memory control signals are used over here, memory write control signal, for example. Okay. So there are interesting things like this. For example, this is the register write signal that we were talking about. You basically propagate the register write signal and also the write register ID over here and use them at the write back stage. So this is another example. Remember, we discussed two single cycle pipelines. Everything is very similar. It doesn't matter. This is the single cycle pipeline over here, and we have a similar selection of boundaries to divide into a pipeline machine. And as we've discussed, this write register signal should be propagated such that you can actually write to use the correct destination ID for the register you're writing in the write back stage. Basically, this is a wrong design because it doesn't have that loop back going for taking the write register ID or destination register ID and putting it back over here. It's really coming from here over here. So you need to actually design the data path carefully to make this work. But hopefully that's all not so hard. And this is another example of the pipeline control. Basically, it's the same control unit as a single cycle processor, except you delay the control to the proper pipeline stage. This is very similar to what I've shown earlier. Okay. Remember the ideal pipeline. Any questions so far? Hopefully this is conceptually simple, but we'll discuss a lot of issues with it. No questions, good. So remember the ideal pipeline, we want identical operations, independent operations, and uniformly partitionable sub-operations. And let's analyze the instruction processing. It violates all of them, unfortunately, but we're still going to design pipeline machines. We don't have identical operations because we have different instructions, and they don't all need the same stages, right? We've just seen an example. Forcing different instructions to go through the same pipe stages adds overhead. This is called external fragmentation, if you will. Some pipeline stages are idle for some instructions. Externally to the pipeline stage, you have fragmentation. This pipeline stage is useless at this moment for that instruction. Uniform sub-operations, again, that's also not true. Basically, we have different pipeline stages, but they're not the same latency. They're not uniformly divided. You're not doing work in that pipeline stage all the time, during the entire clock cycle. So you need to force each stage to be controlled by the same clock. And as a result, you get internal fragmentation. Basically, some pipe stages are too fast, but all take the same clock cycle time. So you're wasting part of your clock cycle while you're in that stage. And these both reduce performance to begin with. And the independent operations, it reduces performance at a different level. Basically, instructions are not independent of each other, not always at least. So you need to detect and resolve these inter-instruction dependencies to ensure the pipeline provides correct results. You cannot ignore dependencies. If this add requires the result of a memory operation, well, you'd better supply that result. Then this causes pipeline stalls. Basically, pipeline is not always moving. Or a pipeline doesn't always have a good instruction to execute because you couldn't move the previous instruction, needed to wait for a result. So that's called a pipeline stall. So these three issues are very fundamental to a pipeline. And you could extend this analogy to, I'm sure, other things in life. So feel free to do that. So issues in pipeline design, basically clearly balancing work in different pipeline stages is critical. Basically, all of the issues arise from here, because it's not an ideal pipeline. So we want to solve them. We want to balance the work in pipeline stages somehow. Now, we're not going to talk about that as much. That's a very tough problem, actually, that people deal with. How many stages and what is done in each stage? We're going to talk about some of this over here. You need to, in the presence of events that disrupt the pipeline flow, like dependencies, control and data dependencies, you need to keep the pipeline correct. Correctness is the first. Moving, that's an example of correctness. And full, that's a performance issue. You need to do that in the presence of data and control dependencies. And also, there's also resource contention. What if you have a register file that's needed by different stages in the pipeline? This is similar to the dryer example, right? Do you replicate that? Or do you order things? How do you handle long latency operations? And how do you keep the pipeline correct, moving and full when you have a long latency operation? If the memory takes 500 cycles, how do you keep the pipeline moving? That's going to be very tough with a beautiful pipeline design that just looks like what I've shown you. You'll need to do something else to be able to handle that very long latency operation. Handling exceptions and interrupts. This is important. If you get an interrupt, what do you do? Because now we've really broken the von Neumann model internally, right? We're not updating the architectural state, but if you get an interrupt, you need to somehow do something about it, right? You need to ensure that the von Neumann model is not broken. The sequential execution model is not broken. And we'll talk about that. And, of course, improving pipeline throughput by minimizing stalls. That's related to this. So what are the causes of pipeline stalls in the last few minutes? A stall is a condition when the pipeline stops moving. And it could happen for many reasons. It could happen because of resource contention, because a resource is needed by two different stages. It could happen because of dependencies or long latency operations. Let's look at dependencies and their types. This is also called dependency, or sometimes it's called a hazard. I really don't like the term hazard because it sounds very dangerous, right? But this is very natural, right? You write programs and you have dependencies in the programs. In fact, you got to have them, right? You need to output something, and that thing is dependent on a previous instruction, right? So dependencies dictate ordering requirements between instructions. And if you don't handle them well, that becomes a hazard, of course. The goal is to prevent those hazards so that you're correct. There are two types of dependence: data dependence and control dependence. And resource contention is sometimes called resource dependence, but I don't like that again because it's really not fundamental to the program semantics. So we'll treat it separately. Let's look at resource contention first. Treat it separately first. Basically, this happens when instruction in two pipeline stages need the same resource. There are solutions to it. Eliminate the cause of resource contention like we did with the dryer. Or use separate instruction and data memories, for example, or caches, instead of having a single cache. Or make multiple ports in that structure such that you can use the resource concurrently. Or another solution is to detect the resource contention and stall one of the contending stages. Now, this is usually not resizable, but if the resource is not used very often, this may not be bad. I'll give you one example. Basically, when Sun Microsystems designed their first Niagara processor, it was an 8-core processor. It had a single floating point unit shared by all of those 8-core processors. And when one core needed, and when two cores needed that floating point unit, well, they resorted to this solution. One core waited for the other one. That's an example, right? Why? Because they didn't want to add floating point units. Now, later, they figured out this is a bottleneck in their design, so Niagara 2 has 8 floating point units. of doing that, or you detect the resource contention and stall one of the contending stages. So if you have only one memory, you need to have an instruction access the memory and a data access the memory. If you have a load instruction that's trying to access memory, and if you have a fetch operation in the instruction fetch stage in the pipeline, this load needs the memory and this fetch needs the memory, but you have only one port to memory, or one memory and one port. Basically one way to access memory. First of all, that's a bad design. If you have a pipeline machine, and if two parts, two stages in your pipeline really depend on a single resource, you'd better duplicate that resource or enable both stages to progress. Because loads are very common, and also fetch is something you need to do every cycle, right? Ideally. You don't want that to be delayed. But in this case, let's assume that somebody designed this bad machine. You can detect this contention. There's a load that's trying to access memory, and there's a fetch stage that's trying to access memory. Who do you prioritize? Well, if you want to keep the pipeline moving, you'd better stall the fetch stage, because the load needs to go out of the machine, right? You've already fetched it. It's trying to access memory. So basically prioritize a later pipeline stage, such that the earlier pipeline stage, like the fetch stage, can move later. Okay. Well, register file has the same issue, actually. But again, it's a bad idea in general to have a pipeline stage stalled because of a resource contention, especially if that resource is needed always, right? Fetch stage always needs a data port to instruction memory. Okay, so there's one example, resource dependence. I'm going to cover this, and we're going to use this sort of figure throughout this course, throughout this lecture. Basically, what's happening here is you have this add instruction, and you have AND, OR, and sub instructions that are dependent on the result of the add instruction. So add instruction writes to the register file over here, and AND instruction needs to read the register file over here, right? Basically, we're going to assume that the register file can be read and written in the same cycle. Well, how do you do that? One way of doing that is you can ensure that this write over here takes place during the first half of the cycle, and the read takes place during the second half of the cycle. There's no problem. Except this guy, one of these guys need a time machine, for example, in this case, right? Because this guy is this add is writing to the register file at cycle 5. Remember, this is pipelined. And this AND is reading from the register file at cycle 3. So clearly there's a data dependency here, and this is not a correct execution order, as you can see, right? So you really need to somehow delay this AND until the result is available. But we will see how we ensure that this is a correct execution order, but not through the register file. If you look here, add actually produces its result on cycle 3, and AND actually needs that result really in cycle 4, right? Because AND happens in this ALU, and add finishes in this ALU. So if you can supply this result directly by forwarding it to the AND, this can be a correct execution order. Okay, but this is an example of resource contention. Let's pull back a little bit. Basically, we're going to assume that write takes place during the first half of the cycle and read takes place during the second half of the cycle. Okay, so if you have this kind of design, the problem is now operations that involve register file have only half a clock cycle to complete the operation. People have done this sort of designs. That's okay.
We're going to have a break now. 10-minute break, okay? Because I want to be on the safe side to finish the lecture. Do you have any questions? If you have any questions, you can ask now, and I can answer. If you don't, you can also ask at the end of the lecture. 10 minutes, please. Okay, let's continue.
When we talk about memories, we can go into more of that. Okay, this is an example of resource dependence, basically. You need to ensure that the stage that writes and the stage that reads don't conflict with each other. And one way of handling it is this way, right? You can be more creative, have 2 ports, right? Okay. So let's talk about data dependencies. Basically, there are three types of data dependencies, only one of which is really real. And the real one is really the flow dependence. It's basically a true data dependence. You have an instruction that needs a result after some other instruction writes that result. That's why it's called read after write. There are also two other dependencies that you need to be careful about in a pipeline machine so that you don't get the incorrect ordering. One is the output dependence. You do a write after write. An instruction writes to a register, another instruction writes to the same register. Now, in a sequential von Neumann machine, which is, the hallmark of which is sequential execution, you'd better get the writes in the correct order, right? The one in the sequential, later in the sequential program order should overwrite the other one. You should not get it in the other order. Otherwise, you'll get a wrong result. Anti-dependence is kind of similar. It's exactly the opposite of the flow dependence. Basically, an instruction reads from a register, and a later instruction writes to that register. You'd better make sure that the instruction that reads from that register doesn't get the wrong value, doesn't get the later value. Well, I'll give you examples of this. So which ones cause stalls in a pipeline machine? Actually, all of them could, potentially. You need to ensure semantics of the program is correct for all of these dependencies. This becomes even more interesting when you do out-of-order execution, when you try to reorder instructions. So flow dependencies always need to be obeyed because they constitute true dependence on a value, right? Because an instruction writes, another instruction reads. Assuming that these are useful instructions, that's a real dependence, right? You're doing an add and a multiply is dependent on it. Whereas these two are not, they're really artificial, right? If you think about it, you write to a register and you write to the register again. What is the meaning of this semantically? Nothing other than the fact that you don't have enough registers. Right? They exist because you don't have enough registers. If you had infinite number of registers, you would never have an output or an anti-dependence. Because whenever you create a new value, you would give it a new name. But for flow dependence, that's really semantics of the program. The program needs to have this result of the add communicate to the multiply to operate correctly. Does that make sense? This is, again, very fundamental. You can think of this as a data flow principle, right? If you remember the data flow graph we've discussed, instructions, you can think of instructions as really things that operate when their data is available. Flow dependencies are basically data flow dependencies. Output and anti-dependencies, they don't exist in a data flow machine, really. Because data flow machine doesn't really have a register file, if you will. Everything is really this graph. You have different arcs communicating values between instructions. Okay, keep this in mind. Basically, they're dependent on a name, not a value. Whereas a flow dependence, you really need the value over there. With the output and anti-dependence, you write to a register, this multiply writes to a register, and later in the program, another add writes to the same register. As long as they're not related to each other in some other way, some other dependent way, there's no relationship between them. Okay, let's look at these pictorially. This is a flow dependence, basically read after write. This instruction needs the value that's produced by this previous instruction. So the data needs to flow from this instruction to this instruction. This is an anti-dependence. Again, this instruction is producing a result into R3. Let's say you store it to memory later on. And this instruction is writing to R1. But this instruction is reading from R1. This is anti-dependence. If you had infinite number of registers, there's no reason why this should be R1, right? Because R1's value is destroyed, basically, at this point. Output dependence, again, same thing over here. Basically here, you have this R3 written by this instruction. You have this R3 written by this instruction again. Again, you're destroying the value that was produced by this instruction and putting it into R3. There's no reason why you should really put it into R3, except you may not have enough registers. So again, write after write is not a true dependence, if you will. So if you think about this, you could really eliminate this dependence by putting the value somewhere else, right? And that's one of the very fundamental concepts of out-of-order execution. How do you make sure this instruction executes before this instruction for some reason? You may think of why. Let's say you have a load instruction that's producing R1. That's taking 1,000 cycles. But the values R6 and R7 are ready. You don't need to wait for them. So why don't you execute this instruction earlier? If you execute this instruction earlier, there's one problem. You may not want to write into R3 because R3 may be needed by some other instruction that's going to be executed later because its value is going to be produced later. So maybe you store this somewhere else. And you can store somewhere else because these really have nothing to do with each other. They're just dependent on a name because compiler didn't have enough registers. Okay, so that's called register renaming, and we'll talk about that when we get to out-of-order execution. But the fundamental reason you can do that is these two things are really specifying in a name there's no value dependence. Okay, any questions? So let's look at the pipeline operation very quickly. I've shown you this before. You have a load and subtract. These go through the pipeline this way. They're independent. Everything is nice. What if the sub instruction were dependent on load? Then you have a problem. Okay, so how do you handle data dependencies? I'll give you some readings first. I hope you're reading. How many of you are reading the book? Okay, excellent. Do you find it useful? Okay, excellent. I think if you do the readings early on, it might be even more useful. But I've also assigned this paper that's a little bit long, unfortunately, and that's not perfect. But it's one of the best papers, in my opinion, that were written, talking about these dependencies, for example, and out-of-order superscalar processors. So it's already on the website. We put it on the website last week, the previous week. So please take a look at that. Okay, so how to handle data dependence in a pipeline machine? As I mentioned, anti and output dependencies are not real, are not true. They're easier to handle in a pipeline machine. Basically, you write to the destination register in one stage and in program order at the end of the pipeline, basically. If you do that, and if you maintain this invariant, you don't have a problem. Okay? Flow dependencies are more interesting because they really cause your stalls, right? I mean, these could cause stalls also, depending on what you do, and we'll talk about that. But as long as you eliminate those stalls, they're easy to eliminate. But these are hard to eliminate. Right? They're there for a reason. And there are 5 fundamental ways of handling these. Let's see how many of these you can name. I'll give some of them. One very primitive way is to detect the dependence and wait until the value is available in the register file. So there's 2 portions of it: detecting the dependence and waiting. Right. Now, this may not be the high performance way, because if we go back over here to this little picture that we had, yes, this incorrect picture. Basically, this add writes its results to S0 in the register file in cycle 5. Now, this AND, when you actually try to read the register file, you need to somehow detect that the data is not there, because there's some previous instruction that's writing into the register file and it has not written yet. So you need to wait until cycle 5. This instruction needs to be stopped. And it needs to wait until cycle 5 when the value is really available in the register file. Sounds like a bad idea, right? Why bad idea? Because we know that the value was produced over here, right? The added S2 and S3 and produced the result over here, when this instruction, even before this instruction, needs that result. So the second is really detecting. You have to detect this situation, and you have to do something about it. That something could be waiting, bad idea. That something could be forwarding the result, which is probably a better idea. So of course you need logic to do that forwarding. Okay, that's the second fundamental way, which is detecting and forwarding, also called bypassing, data to the dependent instruction. Of course, in order to forward, you need to have a path from the end of the ALU to the register file stage. And you need to have a way of detecting that. Right? And that's not enough, because the instructions may not be sequential right after each other. The dependent instruction may be after that. Right? There might be one instruction in between, which is, if you go back to this picture. Oh, there should be a nicer way of going back. Okay, that's not that bad. So if you look at this instruction, this OR over here, this OR needs the result of this add again. And we don't want to wait until the add writes to the register file, because OR gets to the register file stage in cycle 4. Well, how do you get the result? Well, add is in the memory stage, and we know the result. because we produce the result and we're just carrying with it to write to the register file. So why don't we forward from this stage to this stage? So you need to have another forwarding path. And again, the sub also is dependent. It turns out it's a nice example. Basically, at this point, add is writing to the register file and sub is reading from the register file. Assuming this is true over here, write takes place in the first half and read takes place in the second half, then you don't need to do anything. There is no need for forwarding over here. Now, if this assumption was not true, you needed to do forwarding even over here. Okay, so I've given you the idea of forwarding, but we're going to go into more detail. Oh, that's bad. I was going to ask that. Okay, so the second solution is detecting and forwarding data to dependent instruction. Of course, you need logic to do that. You need, again, detecting is common here. The third is detecting and eliminating at the software level. The software does the hard work. Because if our instructions are like that, as I shown you earlier, why doesn't the software actually detect this? They could, at the compiler level, and reorder the instructions such that you don't need to forward or you don't need to wait. Well, how would the software do that? This is where this might be useful. And I wish we had prefetched and powered this off earlier. Oh, well, maybe I powered it on. Okay, let's see. I need something to write with. Okay. Now you're going to have to shout if this is not working well. Somebody said that zooming is a better idea, so we'll try that. Okay, so let's say you have an add instruction that's writing into, I don't know, I like using R's. It sounds like a register, right? And then multiply instruction, that's a terrible multiply. R3, 5, I don't know, R5. And then another add using R5, R5, R6, and then dot, 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 and then an add instruction over here. That's basically, maybe we get rid of the dot, dot, dot. R2, R5, no, I don't like the R5, R10, R11. Okay, you can see this, right? So the compiler can easily do analysis, it's called data dependence analysis, through the code, and basically detects this multiply is dependent on this add, and this add is dependent on this multiply. And it can know that the machine is structured this way. You have a fetch stage, you have a decode stage, register read stage, you have an ALU stage, you have a memory stage, and you have a write back stage. And when you fetch this add executes in the ALU stage, and its result is available. And assume that you don't have forwarding. This add needs to write back over here. So the next dependent instruction should come, how many? 3 instructions after this add. Right? The compiler can know that if it knows the structure of the machine, right? And how the machine operates. Basically, the assumption is that the data is written into the register file at the write back stage, and the data can be read from the register file at the decode stage. So you need a distance of 3 instructions between dependent instructions. So the compiler can say, oh, I cannot put this multiply instruction over here because the machine otherwise would operate incorrectly because it's relying on me to detect the dependencies. So what I'm going to do is I'm going to find 3 independent instructions. Oh, there's one over here. And move it over here. Does that make sense? That way the compiler can ensure that the pipeline is full, because now you're going to put in independent instruction in between. What if the compiler cannot find an independent instruction? There is always an independent instruction. It's called a no-op. Basically, the compiler fills 3 no-ops here if it cannot find any independent instruction, which is essentially a stall, basically, except it's a software orchestrated stall. It's not a hardware detected stall, right? It's beautiful that you can do this at different levels. Of course, it's more powerful if the compiler can fill these slots with independent instructions. Let's say add, multiply, divide, I don't know. If they're independent of all of these over here, that's good. Now you keep the pipeline full. This is a software detection of data dependencies. And a lot of compiler work has gone into detecting and filling these holes, if you will. This is less of an issue if the hardware does more work, right? If the hardware actually is good at forwarding data, for example, the machine model could be, there is a forwarding path from the ALU into the decode stage. So in that case, the compiler doesn't need to do anything, right? The compiler doesn't need, because there is no slot to fill. The compiler can put the multiply after the add, and there is no stall that needs to happen. But if the machine model requires some stalls in between dependent instructions, the compiler can improve performance by finding independent instructions and putting it inside there. Now, how does the compiler find the independent instructions? First, it needs to do this data dependence analysis, right? And then do the movement of instructions. The problem is moving the instructions may lead to breaking the program semantics, right? Especially if you're trying to move instructions across control flow boundaries. That's always a danger, right? So if you have this instruction in a branch, and you have two paths over here, and then you have something like this. If you move an instruction from here to here, what if the branch goes this way? Oh, so the compiler needs to be really careful. If you move an instruction from here to here and respect the data dependencies, well, maybe it's safe, right? It may be okay, as long as you reach this point. What if you don't reach this point? What if the machine gets interrupted before that? Or what if you get an exception, or you can be in an inconsistent state? So there are rules for moving code, both upward and downward. And that has impact on not only performance, clearly it has an impact on performance by filling these slots, but also correctness of the program. So the compiler needs to be really careful in doing this movement. And we're not going to cover this in class, but if you take a compiler's class, or if you take my advanced lecture, there's a lot of theory and practice in static code scheduling. So if you, for example, compile your code with -03 in GCC, you will get a lot of these code movements to ensure that the pipeline is flowing. Okay, so it's beautiful. This is beautiful because it doesn't need to do anything, which is the philosophy of MIPS, right? No need to for the hardware to detect the dependence. Okay. So there are two other ways. These are maybe obvious, right? What are the two non-obvious ways? What else can you do? When you get a dependent instruction, anybody brave enough to?
Insert some kind of barrier instruction that prevents reorg, or like, I don't know.
So that's more like basically inserting a no-op, basically, right?
Yeah,
You could potentially say, basically, compiler can inform the hardware, or there's a dependent instruction, and you need to do something about it. It's similar to no-op, I would say. Yes?
If there's a branch instruction, you can predict which branch you take, and if you took the wrong one, you just flush.
That's right, yes. So prediction, basically. You had the same idea, or? Okay, excellent. So basically predict. Branch is a special case. But you can predict the needed value, right? It can be any value. Now it turns out branches, at least conditional branches, require a small prediction space. You need to predict whether it's taken or not taken. You need to choose from only two choices. And you need to know the target address. Usually it's easy to compute if you've taken the branch once. But doing it for arbitrary data values may be a little bit difficult, basically, right? So you predict the needed value and execute speculatively and verify. This is an interesting choice. It's called value prediction. In the case of branches, it's branch prediction or control flow prediction. But this is another possibility. What else? We're not going to cover this in more detail. Again, you can take the advanced course. In some cases, this works really well, actually. Actually, let me tie this in with something that we've started early on. If you can afford to be approximate, and if you have a good value predictor, most of the time you predict the value and you keep the pipeline flowing. And if for some reason you get it wrong, it may be okay, right? assuming your program can tolerate it again, right? That way you get rid of all of these memory accesses going to memory. Right? Okay, it's fun. It's fun to be an architect because you can play with a lot of these ideas. What is the last one? Last one is my favorite, actually.
Actually, the last one, as you can see in the slide, do something else, is fine-grained multi-threading. You have, at the end of the slides that I have already uploaded to the wiki, you will find some backup slides about fine-grained multi-threading, and this is something that Professor Mutlu will explain in a later lecture. But now we're going to continue with the three first possibilities that he has explained.
Well, let's take a look at some other ways of handling data dependencies. So detection. Fine-grained multithreading is beautiful because it doesn't require you to detect, but if you want to improve single-thread performance, you got to do the hard work. And the hard work requires detection. It's also called interlocking. Basically, it's the detection of dependence between instructions in a pipeline processor to guarantee correct execution and also enable high-performance execution. So we just discussed software-based interlocking with this code example. Software detects, and hardware can be really simple. Of course, there are downsides and upsides. We can discuss that, or you can think about that, but we don't have enough time to cover all of those. But we'll talk about hardware-based interlocking. How do you detect? Actually, before that, I guess MIPS acronym. This is essentially MIPS. MIPS was initially designed for software doing the hard work. Microprocessor without interlocking pipeline stages. Software does the interlocking, hardware doesn't do anything. Of course, if you look at the latest MIPS processors, they all do hardware-based interlocking. Because for high performance, it's very hard to do it just at the compiler level. You need to do it cooperatively. Okay, so how do you detect the dependencies? We'll go through this relatively quickly. You can think of many ways, but one way that's been used is scoreboarding. Conceptually, it's very nice. Basically, each register in the register file has a valid bit associated with it. An instruction that's writing to the register resets the valid bit when you decode it. In the decode state, you reset the valid bit. An instruction in the decode state checks if all its source and destination registers are valid. If it's true, it can progress. It doesn't need to stall. If it's false, you need to stall the instruction. Now you can optimize this. You can ask why do we check the destination? Well, you need to ensure that write after write dependencies are also obeyed, right? The advantage is very simple. It's basically 1 bit per register. The disadvantage is now you need to stall for all types of dependencies, not only flow dependencies, right? Now you can think of how do you actually fix this? Well, maybe you don't check the destination register if it's valid, but you ensure that destination register is written at the end, right? But then a single valid bit may not work. What if you have multiple instructions writing to the same destination register that are further into the pipeline? Right? You need to have a counter then, right? Because multiple instructions may be writing to the same register. So you cannot just reset the valid bit when one instruction writes. You need to decrement the counter. You need to ensure the latest value gets into the register file. So if you design a pipeline processor, you will figure this out. Okay, basically, I've just given you the answer to that question. What changes would you make to the scoreboard to enable not stalling on anti-output dependencies? Was that clear? Maybe you can think about it on your own a little bit. But basically, if you have a single valid bit, it prevents the progress of all instructions, all dependencies. Okay, so there are other approaches, which is combinational dependency check logic. You add special logic that checks if any instruction at a later stage in the pipeline is supposed to write to any source register of the instruction that's being decoded. If the answer is yes, you stall the instruction in the pipeline. Right? Basically, you have these later pipeline stages. Actually, this is probably better to... okay, I'm not sure if it's too complicated. I'll just draw it quickly. I'm going to give you examples of that. You have this fetch stage, you have this decode stage, ALU stage, memory stage, and write back stage. And you can hopefully see. So basically, an instruction needs to wait for its operands here. An instruction, well, I'll just put the pipeline registers, why not? My ugly pipeline registers. So an instruction may be writing to register X over here, write to register X. Another instruction may be writing to register, I don't know, Y. Another instruction may be writing to register Z. In order to stall this instruction, well, let's ignore the write back part, because write back actually can, we're going to assume that the register file, you can write to the register file and read from the register file in half cycles. Let's ignore that for now. Basically, in order to stall this instruction, you need to check if the source register A and source register B somehow equals any of these registers, right? Basically, that's a combinational dependence check logic. And I'll just show you how to build that logic. Is this equal to this? Or this? Okay. Color is good. And is this equal to this? Or this? And if any of these evaluate to true, you have an OR gate, an ugly OR gate, you basically generate a stall signal, right? You stall this instruction. If any later instruction is writing to any source register, that's the idea. And you can see the complexity of this now. If you have more pipeline stages, you need to check all of them, right? So this combinational logic can become your critical path easily, because you need to see which instructions are writing to, if any of the later instructions are writing to any of the source registers over here. Okay, but there's actually more complicated things are done, so it's doable. So upside is no need to stall on anti and output dependencies, because you just check for flow dependencies. There is no reason to check for anti and output dependencies. Those are easy to handle, as we discussed, right? You write to the destination register at the very end. The disadvantage is logic is more complex, and logic even becomes more complex as you make the pipeline deeper and wider. Well, what is wider? Wider. So deeper means you add more pipeline stages. Let's assume that you have 30 stages over here to increase your clock frequency. That may or may not be a good idea, but if you have that, now you need to do this logic increase in complexity. Now you can also go wider, meaning you have another fetch engine over here fetching from, you basically do parallel fetch from sequential instructions, right? You fetch instruction number 1, 2, 3, 4, 5, and then you basically fetch 5 instructions per cycle. Now if you do that, you need to check dependencies between these instructions also, right? Not only in the horizontal dimension, you need to check dependencies in the vertical dimension. Assume that this is the oldest instruction that you're fetching, and this is the youngest in the same cycle. You need to ensure that the youngest instruction obeys the dependencies, right? So it becomes a very complicated dependency check logic as you increase the pipeline depth, as well as the pipeline width. So if your pipeline depth is 20 and your pipeline depth is 6, which is not unreasonable today, you have 120 different combinations of dependency check. Of course, you can eliminate them, some, because not all of the, at the end of the pipeline, you may not need to check the dependencies as we just seen over here with the write back stage. But it becomes complex. And this is also done in superscalar out-of-order processors today. Okay, so this is called superscalar execution, making such that you can fetch multiple instructions per cycle. It's called superscalar execution. So it's not scalar, not a single value. It's superscalar. It's multiple different instructions from the same thread. Okay, once you detect the dependence in hardware, what do you do afterwards, right? We've covered some of these, but we'll go into a little bit more detail right now. Basically, dependence between two instructions is detected before the communicated data value becomes available, right? The option 1, this slower option, stall the dependent instruction right away. As we discussed, it's a bad idea. Option 2 is stall the dependent instruction only when it's really necessary. Basically, forward the data from the appropriate stage. And there could be other options. So what is data forwarding bypassing? A consumer instruction has to wait in the decode stage until the producer instruction writes its value into the register file. That's the problem we're solving. We don't want to stall the pipeline unnecessarily. So the observation here is that the data value needed by the consumer instruction can be supplied directly from a later stage in the pipeline, instead of only from the register file. Basically, supply the data value when it's produced. And this should remind, basically the idea is to add additional dependence check logic and data forwarding paths to supply the producer's value to the consumer right after the value is available. The benefits, the consumer can move in the pipeline until the point the value can be supplied. Less stalling. So you don't need to wait until the value is written into the register file. So this is actually very aligned with the data flow principles. We're going to see another slide, right? Basically, data flow says the data should be supplied when it's ready. In that case, you fetch the instruction. In this case, we're still in a von Neumann machine. Basically, when you supply the data directly when it's produced, it's the closest amount of delay that you induce on the instruction that's dependent, right? So data forwarding is a very limited application of data flow into the von Neumann model. Very limited. Okay, a special case of data dependency is control dependence, as some of you have talked about. This is basically, can be thought about data dependence on the instruction pointer, program counter. It's essentially another register, right? And the question here is a little bit different because that determines what you fetch. So what should the fetch PC, fetch program counter, be in the next cycle? Answer is address of the next instruction. The question is, what is the next instruction? All instructions are actually dependent on the previous ones in a sequential machine, right? Because you need the program counter value to be calculated to be able to fetch the instruction, next instruction. Now, in most cases, when you're executing sequential, this is trivial. You actually know what instruction that is. It's PC plus 4 in MIPS, right? The instruction at address PC plus 4. So the problem happens if the fetch instructions, if the fetch instruction is a non-control flow instruction, next fetch PC is the address of the next sequential instruction, which is good, which can be easily computed. So assuming that you always go to the next sequential instruction is one form of predicting the control flow, right? Saying that, oh, next instruction is likely the next sequential instruction, so I'm going to increment the PC and fetch from it. The problem happens, the problem happens if the instruction that's fetched is a control flow instruction. How do you determine the next fetch PC? Well, how do you even know that it's a control flow instruction? You haven't even decoded it yet, right? You're fetching. Whereas decode comes later in the pipeline, right? So this problem has fascinated many people, and many people have worked on predicting what should be the next instruction to fetch. And modern processors have very, very sophisticated branch prediction engines that use many different components to be accurate. And in many cases, they're as accurate as 97, 98%. So 98% of the branches are predicted correctly. But there are some programs where the prediction accuracy is much lower, of course. Especially the branches that are dependent on incoming data is very difficult to predict. So this could be, if we had more time in this class, we would cover branch prediction, but we're going to cover really the basics. The much more advanced branch prediction methods we're going to leave for the advanced architecture course. But people have made a lot of money from Intel to actually make this work. Let me put it that way. It's a hard problem. It's one of the hardest problems in computer architecture in a control flow machine. Okay, well, there's another thing that I skipped over here, but I think this is also important. This actually makes life a little bit more complicated because if you know the size of the fetched instruction, that's good. But if you have a pipeline machine, and if you don't know the instruction size, if you have variable length ISA, if your instruction set architecture doesn't have fixed size, fixed length instructions, you have a problem. You don't need to, even the next sequential instruction you don't know. Because you don't know the address, because you don't know what the length of the currently fetched instruction is, right? Because you haven't decoded it yet. Only after you decode it, you know the size of the instruction, right? x86 is a variable length ISA. An instruction can be 1 byte or 17 bytes, depending on a lot of things that happen during decode. You figure it out during decode, basically. So next instruction to fetch, the address, even the address you cannot determine, even if it's sequential. Right? How do you do that? Well, that's the beauty of designing a machine with a complex ISA like that. Okay. Let's go into a little bit more detail. So we know this right now. Flow dependence, anti-dependence, out-dependence. You should know this very well. I think this is a figure that we've seen earlier. Basically, it's very similar to what I've shown before, except they were not adds. But basically, this add produces a value, RA, register A, and all of the instructions are dependent on it. And we don't care what other registers are. So for this pipeline to work correctly, this is where the name hazard comes from, actually. This is hazardous, right? You need to ensure that this instruction doesn't get this value over here until this instruction writes back. But this instruction is safe, assuming you can write to the register file in half cycle and read from the register file in the next cycle. So how do you resolve the data dependence? Basically, you can insert bubbles, right? But we don't want that, as you know, right? So what is a stall? To define a stall more formally, actually, you can, I'm not going to be formal in this course, but you can define a lot of these things very, very formally in terms of whether the pipeline should move based on this distance between instructions, and how do you make sure this is correct? And people have dealt with formalism in the 1970s. I'm not going to bore you with that. I'm just going to give you the insights. But you can define all of these very, very formally and prove characteristics of whether or not a pipeline is correctly moving, executing instructions. It's much more difficult to prove the performance. So we're going to talk more about the performance aspects, because it's very difficult to do that formally, at least right now. But basically, stall means make the dependent instruction wait until its source data value is available. In the hardware implementation, you need to stall all upstream stages and drain all downstream stages. Upstream meaning the younger instructions that are being fetched. Downstream means older instructions that you need to get out of the pipeline. Basically, you need to drain the pipeline and stall the upstream. We'll see that. Basically, this is one of the machines that we've looked at. How do you implement stalling? If you discover that this instruction is dependent on some other instruction later on, and you don't have the value in the register file, or you cannot bypass the value, you disable the program counter. You don't write to it. And you disable this instruction register such that this instruction stays over here. You don't write to it. And you keep the other instructions moving, but you should ensure that this instruction cannot move now. It needs to wait. But what do you inject over here? Well, you inject a no-op. Right? This is basically a hardware-injected no-op, as opposed to a software-injected no-op that we've seen earlier. How do you inject the no-op in hardware? Make sure this pipeline register is invalid. Right? This is called a bubble again. How do you do it invalid? You can have a valid bit associated with it, and you can set it to 0. You can clear the control signals such that they reflect a no-op. That's another way of doing it. But there are multiple ways of doing it. I like the valid bits because that when you inspect the pipeline, you can easily see, oh, this pipeline register is not valid, meaning that it's carrying something that's garbage. It's not going to have any effect. So from a testability and design perspective, it's more principled to have a valid bit, in my opinion. Because now when you actually are trying to debug this pipeline, you can check that valid bit. It's a lot harder to inspect all of the contents of the control signals to conclude this is a no-op. Again, you may save a bit, but saving a bit doesn't always save you time later on. So if you think about design for testing this machine, it's always better to have the valid bit over there. Okay, so this is the data depends example that we've seen before, or at least something similar to it. I hope you can see this over here. But basically, this is the wrong thing. This add writes into S0 in the first cycle of cycle 5, and this AND reads S0 on cycle 3, or reads S0 on cycle 4, subreads S0 in the second half of cycle 5. So this is correct, but these guys are not correct. So clearly, this is a wrong pipeline. That's why this is a hazard. But we don't want hazards. This is the example of compile time detection and elimination. If you want to eliminate this potential hazard, if you will, the compiler inserts 2 no-ops, and life is beautiful again. Except you wasted 2 of your slots. You reduced your cycle, you've increased your cycles per instruction overall, right? So no-ops are bad. You actually increase your instruction count also. So you know the equation, right? The performance equation. This is fun. If we can find the performance equation, you can probably recite that if I ask you in an exam. So execution time, can you guys see it? Oh, we need a light, I think. Okay, that's better. Equals, with my terrible writing, number of instructions times cycles per instruction times clock cycle time, right? So if you inject no-ops, you're increasing the number of instructions, and you're increasing the CPI, right? Well, this, I'm not sure. I mean, you're definitely increasing the number of instructions. You can think of it that way. So basically, you're increasing the execution time, right? So this is a bad idea in general. Of course, you can think about how to compare. So as this works, this execution time equation, my point is this execution time equation works if the work is the same. Here, you're really increasing the number of instructions with a no-op. So one way of reducing the execution time is by eliminating no-ops, for example, right? So if you have a bad compiler, you can always improve its performance by eliminating the no-ops. But that doesn't mean that you're starting with a good baseline. So whenever you see a lot of no-ops, it's probably a bad baseline. That's my point over here. So be very careful. So okay, inserting enough no-ops for the required result to be ready is the idea of software-based interlocking. Basically, or as we discussed earlier, if you can move the independent useful instructions up, it turns out that's a difficult task. And we're not going to cover that. So data forwarding, data bypassing, we've already covered this briefly, but I'm going to give you the mechanics of it. And the basic idea we've seen in data flow. Forward the result to the value to the dependent instruction as soon as the value is available. Basically, in data flow, data value is supplied to the dependent instruction as soon as it's available. Right? Instruction executes when all of its operands are available. So data forwarding brings a pipeline closer to data flow execution principles, but just by this much, perhaps. So this is the concept of data forwarding, illustrate a little bit more. If you look at this, now the data value is available here. You can bypass it, you can latch the data value and bypass it directly into the input of the ALU, right? Or you can bypass it directly into the other input of the ALU. That's the idea. So in order to be able to do that, you need to have additional dependence check and detection logic and additional muxes also. Now the input of the ALU doesn't come only from the previous stage where you read the register file, but it could also come from the latched value of the output of the ALU, a previous add, or it could also come from the latched value over here, right? If you look over here, yeah, basically you need to forward from these two different paths into the input of the ALU. And also both inputs of the ALU, and you need to have this dependence check logic that we've drawn over here, the little monster of comparators that basically check for dependence, whether you should forward, which value you should forward, and whether you should forward. So this part of the machine becomes more complicated, as you can see. Okay, I think we've discussed this basically. You forward to the execute stage from either the memory stage or the write back stage. When should you do that? I think we've already discussed this. If that stage will write a destination register, and the destination register matches the source register that you're trying to read from. And if both of them contain matching destination registers, then memory stage should have the priority because it contains the younger instruction, right? You should always forward from the youngest instruction because this youngest instruction overwrites the value that's written by this one. Now it's a concocted example over here because this may write to the register 5 and this also writes to register 5. Then this value is kind of dead, right? You've overwritten register 5. Okay, so you can study this on your own, but it's conceptually pretty simple. So stalling, as we've discussed, so let's assume that we have data forwarding. Can we eliminate all of the data dependencies that way by forwarding? Unfortunately not. Basically, forwarding is not always sufficient because there are cases when forwarding is not possible due to pipeline design and instruction latencies, even in this really, really simple pipeline. So that trouble over there indicates that you're executing a load instruction. The load instruction has its value produced right at this point, right? Now this AND instruction needs that value right away, right? Now you could potentially do this forwarding, right? But there's a downside to that. If you actually forward the data from the output of memory input of the ALU directly, what did you do? Any thoughts? Yes? You increase the critical path. Exactly. Yeah, you increase your clock cycle time. There's a reason why this is just memory. There's a reason why this is just ALU. If you forward the data value produced from memory to ALU in the same clock cycle, your clock cycle has become like the sum of both of those operations now. So you could do that forwarding, yes. In this case, it's not really forwarding, but it's because you're essentially lengthening the pipeline stage. So that's a bad idea. So without lengthening the pipeline stage, there's no way you can forward the data value because the data value is over here. But by that time, the end instruction would have executed. So here, there's no way to supply the value with data forwarding. Because, this is written over here. So what you need to do over here is stalling. And in order to implement stalling, you need to detect that data dependence and wait. Okay, we're going to pick up from here and continue tomorrow.
That's what we are going to do. We'll continue tomorrow. Do you have any questions? Okay. Thank you very much. See you tomorrow.